Well, let's do a little bit of a bonus episode on swimming, kinematics, and combining kinetics. So what I want to do is go through some information that was presented in the swimming kinematics session and go a little deeper on that. And I did mention to go back and watch some of the swimming kinetics information that we've gone over. And now I want to try to combine those two stories into one. So we're going to think like a biomechanist. Oh, I think it's a great 80s song. Or maybe that's Walk Like an Egyptian. I don't remember. All right, so let me go through the slide that I'm interested in. I want to talk a little deeper on. All right, so here's swimming velocity for the cross stroke. Now, there are different velocity profiles for different swimmers, and swim technique will influence this velocity versus time profile. There's different velocity versus time profiles for different strokes, breaststroke, butterfly, backstroke. And what's interesting is the wearable technology is taking advantage of these different profiles and using smart devices to detect different types of strokes. And so you can wear goggles that are instrumented with accelerometers. You can wear a watch that's instrumented with accelerometers. You can wear a chest strap. There's the hand strap that I've been wearing, measuring swim force, all taking advantage of the different profiles of these different strokes to then categorize them, put the data through an algorithm and categorize them as different strokes. All right, so that's interesting. What I want to talk about in this video is why velocity is changing. To understand how velocity changes or why velocity changes, we need to go into kinetics. Kinematics is just a study of motion. It's a description of velocity versus time pattern, for example, during swimming. And there's some use for that, just as I just described. But let's go a little deeper and match up our kinetic information with the kinematic information. So let's look at this a little bit more. Velocity is never constant during swimming. Now, sometimes I'm guilty, and others are as well, is saying, well, let's consider a situation where velocity of a task is constant. There's very few tasks where velocity truly is constant. But what we're doing is we're simplifying the problem. And I'm guilty of that as well, because we need to go through concepts and then work towards situations that are more complex, like this. And this is actually simplified as well. This is just presenting information in one dimension, all right, just the horizontal dimension. There is vertical movement of the swimmer. There is also side-to-side movement of the swimmer. So really, we would need to do this analysis 3 times or come up with a way to look at the 3D kinematics and kinetics at the same time. That gets a little challenging. The math gets a little deeper as we do that, but it's doable. But let's continue to be lazy, and we'll build on things. So we'll go away from the situation where velocity is constant and move to a situation where velocity is not constant. Why is velocity constant simplifying the problem? Well, constant velocity means zero acceleration. Remember, zero acceleration simply means velocity is not changing. So now if you think about Newton's second law of motion, add up all the forces acting on the object, and that equals the product of mass of the object times acceleration. Well, once you set acceleration to 0, that takes away the right-hand side of that equality sign. So now you just have all the forces to deal with, and you start looking at how all those forces add up to 0. So it ends up being a little simpler problem to deal with. But now we don't have that situation in reality. And again, I'm just looking at one dimension. I'm just looking at horizontal movement, and I'm looking at horizontal movement in the direction of swimming. I'm not looking at side to side. Ultimately, to understand swim technique, we do need to do all 3 dimensions because they are each important in their own way. But here's velocity, slowing down while moving forward, speeding up, moving forward, slowing down, moving forward, and so forth. We can look at how fast velocity is slowing down or how fast it's speeding up, and we can see different regions where velocity is speeding up quite fast. And then we can look at the swim stroke to try to understand why that velocity is changing. Well, it has to do with kinetics, has to do with forces. And same thing, why is velocity slowing down at a greater rate here? Why is there a greater negative acceleration here? This is a positive acceleration, negative acceleration, and so forth. All right, so let's switch cameras. And let's go to the drawing board, literally. Get my marker out, get a marker here. All right, well, let's go back and do a kinetic analysis of swimming. You should be very comfortable with doing this type of analysis where we're identifying all the forces acting on the object. In this case, we're dealing with swimming. I'll try to draw a swimmer. I'm not great at drawing swimming. Okay. And here's the water level here. And here's the two arms for the swimmer. What forces are acting on the swimmer? Well, let's remember there's gravity, that's vertical force, and we have a buoyancy force, both vertical forces. We have a resistance force. I'll just draw this at the head. I'm going to make it a thick line and a thick arrow just so we can see it on my drawing. Okay, so we have some resistance force, and we have some propulsive force. Now, I'm only drawing one propulsive force, and I'm drawing it at the hand. And again, we'll simplify, and then we'll add in more information as we get deeper and deeper into understanding swimming. We do have the legs, which do contribute to propulsion. Likewise, with resistance, I'm drawing just a single arrow here, but the resistance is coming from throughout the body, okay? So right now we're dealing with just one propulsive force and one resistance force. Now in our kinetic analysis, we do sum of forces acting on the object equals mass times the acceleration of the center of mass. And in this case, I have a propulsive force acting in the same direction of movement. And I have a resistance force opposing the direction of movement. And that's it. Oh, I should have said, let's deal with the horizontal. And we'll deal with anterior posterior, okay? Like I said, there is vertical movement of the swimmer. There is this undulation that swimmers take advantage of and actually help with propulsion, but right now we're going to just look at anterior posterior horizontal movement. And likewise, if we look down on top of the swimmer from the back, we would see side-to-side movement, and that would contribute to resistance. Yeah, I don't think it really contributes to propulsion, but it does contribute to resistance. So maybe it would contribute to propulsion if we're trying to position the body in the right place to generate the best horizontal anterior posterior propulsive force. All right, but we're going to deal with this right now, okay? So now I have these two forces. And this is our equation that we need to use to explain why velocity is changing during swimming. All right, so let me pull that up and let me redraw that velocity profile from the graph. Now I'm not going to do any negative velocity because the swimmer is only moving forward. And what we had is the swimmer slowing down, speeding up, slowing down, speeding up, and what have you. That just continued. You should be very comfortable with explaining how velocity changes, where this is slowing down while moving forwards. Now, for those of you who've taken a biomechanics class with me before, you know when I ask what's happening kinematically, I always look for two pieces of information: what's happening to velocity and what direction is movement. In this case, this is slowing down, moving forward. This is speeding up, moving forward. This is slowing down, moving forward, speeding up, moving forward. And we would know, if I come down here to acceleration, I can generate my acceleration profile. Just draw some dotted lines down from the peaks, because I know the direction of the slope of the velocity versus time plot changes from being negative to being positive to being negative and then positive again. So I have periods where acceleration is negative and periods where acceleration is positive. I'm not going to draw the graph right now because sometimes that ends up being distracting, and we are drawn to trying to explain why acceleration magnitude is changing over time. First level, I always like to deal with why is acceleration negative here? Why is it positive here? Well, it's negative here because we're slowing down, moving forwards. It's positive here because kinematically we're speeding up, moving forwards. Okay? Well, let's think kinetically. Why is that the case? Well, let's go back to our equation. I won't derive it here. I'll just write the equation that we just derived in the previous page. That's our kinetic equation for swimming. So why is acceleration negative? Well, mathematically, it has to be negative because the resistance force is greater than the propulsive force. It's that simple. Why would acceleration be positive here? Well, mathematically, if this is positive, if the right hand, and mass is always positive, measure of inertia, an object's resistance to change movement. If acceleration is positive, this product is positive on the right-hand side of the equality sign. That means the propulsive force has to be greater than the resistance force. Has to be. All right, so there's this interplay of these two forces that explain why acceleration is either negative or positive. Propulsive force is either greater or less than resistance force, and therefore that drives acceleration. And because we're only moving forward, we can then look and see what's happening with velocity based upon that understanding. So slowing down, moving forward, speeding up, moving forward. Why are we speeding up, moving forward? Because the propulsive force is greater than the resistance force. Why are we slowing down? And this is a steeper slowing down than over here. Why are we slowing down at a greater rate here? That would mean a greater negative acceleration. That would mean this product on this right-hand side of the equality sign is going to be bigger than maybe over here. That means the resistance force has to be much bigger than the propulsive force. So when you start using this equation and the kinematics together to understand what's going on, you're starting to really think like a biomechanist, right? And this is a really easy way, you'll see. And you should be able to do this with biking and running as well. And so maybe practice that. I'll do a bonus episode for each of those sports down the road as well. But you should be comfortable with combining the kinetic analysis with the kinematic information to explain why movement is occurring the way it is occurring. But now let's dive just a little deeper and let's look at these forces a little bit more. I got another piece of paper. So let's look at propulsive force. Well, where is the propulsive force coming from? Well, we dealt with this before. And this propulsive force during swimming is a drag force. Remember, if you're trying to row a boat, you put your paddle in the water. You're not trying to move your paddle through the water. You're trying to move your boat beyond the paddle. Ideally, your paddle stays in one place and your boat moves beyond the paddle. If your paddle starts to move through the water, well, then your boat's not going to move very far forward. Same thing with swimming. You are pushing against the water, and the water is pushing back on you. And the amount that it pushes back on you is because of a drag force. Now, remember, these two forces, if acceleration is 0, these two forces can be equal and opposite to each other. That is not Newton's third law, okay? Newton's third law, I haven't even mentioned. Newton's third law says for every force acting on the person, there's an equal and opposite force, not in this equation. So there's another equal and opposite force to this. There's another equal and opposite force to this. All right? Let's not confuse Newton's third law with anything we've done so far. So the propulsive force is a result of the drag force. And we know the equation of a drag force. So I'm going to write it out here. 1/2 rho CdA v squared. And I'll do this because we're going to need this equation again. This is the density of the fluid. All right. CD is the coefficient of drag. And be sure to go back and listen to the drag force equation video. The CD is influenced by, in essence, the shape or how well and overall the fluid moves over the object. And then A is the frontal area, or it's the area perpendicular to the flow of the fluid. And V is the velocity of the fluid. It's not the velocity of the person, okay? But it's the velocity of the fluid moving over the object, or the person in this case. Now, in essence, in swimming in a pool, you would think that the velocity of the fluid and the velocity of the person are in essence the same thing. And for the most part, they are. But there are pools that have been accidentally designed that either aid a swimmer or slow a swimmer down based upon how a current may be generated within the pool, either due to the jets that push the water out into the pool based on the filtration system, or the way that the pool is designed and the sides are designed, and other swimmers swimming, there's ways that other swimmers can influence the velocity of the fluid acting on the person. So this is not always the velocity of the object. This specifically in the equation is velocity of the fluid. Also remember, because it's hard often to separate out these two terms, we collectively refer to them as CDA. Right? It sounds like three terms, but it's two terms: coefficient of drag and frontal area. All right, so now, how do we increase the propulsive force? How do we get to a situation where the propulsive force is much greater than resistance force? Well, one way to do that is to increase this FP. How do we increase that FP? Well, let's not talk swimming yet, because I don't expect any of you to be a swim coach. But now, here we are. Let's think like a biomechanist. How do I increase this propulsive force? I have to increase something in this equation. Well, if I'm just dealing with swimming in a pool, I can't do anything about the density of the fluid. But if you're starting to look for a pool to swim the fastest, or a body of water to swim the fastest, you may want to consider the density of the fluid. When we start looking at saltwater swims for triathlon or freshwater, that may actually come into play. But nothing you can do about it other than swim in it. CD and A collectively, we may be able to do something with that. And V, velocity of the fluid, is really going to be a function of, it is going to be related to how fast we're running, but it's also a function of swim technique, right? So let's tease this out a little bit more. How do we influence, CDA during swimming? All right. Well, this could be, and I'm just going to start listing some factors here. It could be hand position in the water. Now remember, swimming is really a three-dimensional movement, but I put my hand in, I can turn it, I can pitch it, I can put some rotation on it, I can put some yaw on it. The hand position can ultimately influence how well the fluid moves over the object or doesn't move over the object. And it can also influence the frontal area that the hand is pushing on the water. So swimmers will spend a lot of time working on hand position in the water at different points of the stroke, right, in order to maximize, or in order to increase this propulsive force. I could put on something that increases the frontal area specifically, like a hand paddle. That's a swim device that swimmers use, or maybe some gloves that people will use for increasing the frontal area of the hand. That's what that's going to do. If that increases A, that is going to increase the potential to increase propulsive force. Let's see, those are the two big ones I want to do, and that's increase in propulsive. Well, actually, it could also be something with not just the hand, but maybe the forearm. Okay? Maybe forearm and hand put together. Maybe there's a way that you can have a specific technique to increase this CDA, to increase propulsive force. And again, now we're going to start getting into, coaching. And how do we set up our swim stroke in order to increase the CDA as much as possible for the hand? Or if we go to the kick, now we would start looking at factors that could influence the CDA of the kick as well. All right, so this is propulsive that we're dealing with. All right, let's go the other route and look at the resistance force. This is probably, the propulsive, boy, it takes a lot of coaching, it takes a lot of video of swim stroke, trying to get that technique to maximize, in essence, the CDA of the swimmer. Now let's look at resistance force. Where's the resistance force coming from? It's coming from the drag force again. So FR is going to be equal to the drag force equation again. 1/2 rho CDA V squared. Same parameters. All right. Nothing to do with Newton's third law. Same equation. So now we can't do anything about the water again. The V is in essence going to be related to how fast we're swimming now, because now the faster we go, the more resistance we're going to get due to the drag force. It's like driving in the car. If you put your hand out the window, you start speeding up, you're going to feel that air pushing against you greater because that fluid is moving over the object at a faster rate. But let's zero in on the CDA again. What will influence the resistance force? Well, it's any of these factors, but I'm going to zero on CDA. Well, now it could be, I'll do horizontal position. Something swimmers are often trying to work against is avoiding where the person, I'm trying to do a person swimming with the lower extremity too low. Because if you take the frontal area, looking in at the swimmer, by dropping the legs, that's going to increase that A parameter. By dropping the legs, increasing the A, you're going to increase the resistance force. Increase the resistance forces, we're back over here. You're going to increase this, which means you need more propulsive force to speed up. Or if you can only generate so much propulsive force, if you increase the resistance force, you're going to slow down a lot more. So you have a lot more undulations in swimming velocity. So horizontal position. How do you influence horizontal position? Well, it is technique, and you're learning how to swim, but you could also add buoyancy. Now this comes back to the third dimension, or at least the second dimension, buoyancy force, a vertical force. You could use a pull buoy, or you could use a wetsuit. Anything that brings those legs back up in the horizontal position. And again, this is where we start to cross over into another dimension. But we want to reduce this A, we want to reduce that horizontal position. All right, what else can we do for reducing resistance force? Well, that's, wear a swim skin or a race suit AKA, I guess, or even a wetsuit. These are all designed to reduce CD, the coefficient of drag, specifically. Now, the wetsuit also decreases A because it also brings your lower extremity up. But it's really focusing in on reducing CD. It's the fabric is smooth. The water moves over the fabric easily. It does not allow the water to stick to the skin, and therefore reduces the coefficient of drag. There's also a bit of compression that happens. And this is actually something I've been fortunate enough to work with a wetsuit company a bit on this. And this is actually something that seems to be really important from a wetsuit, is the amount of compression that's going on. That is likely also reducing CD, because if you ever watch someone swim underwater, your adipose tissue actually does oscillate as you move through the water, and that oscillation can ultimately increase CD and therefore increase the resistance force and slow you down. Swim skins are built the same way to reduce CD, and they're also really hard to put on, and they are providing some compression there as well. And the race suit, I should have put AKA, really something you use specifically for race. Now, in training for swimming, often a swimmer will increase the CD by wearing loose fabric, loose clothing, and that therefore forces them to generate more propulsive force. So it's a little bit of a training technique. All right, but now we are focusing on reducing CD. Well, why do we want to reduce CD? Because it's part of this equation. There's CDA. If I can reduce the resistant forces, I have less force opposing the direction of movement, and therefore whatever propulsive force I can generate, I'm going to be generating more acceleration, and because we're moving forward only, we're going to be able to speed up more. So how do we swim faster? This equation right here. I reduce my resistance forces, I increase my propulsive forces, but there is this interplay between these two forces, because you are never just speeding up during swimming. You are slowing down, speeding up, slowing down, speeding up. You're always slowing down, speeding up. So there's this interplay between these two forces. How do you increase propulsive force? Well, you just go to your equation, your drag force, and you go through each of those parameters, and you identify how you can increase each of those parameters. How do you reduce the resistance force? Well, you go to that equation, there it is, and you try to reduce those parameters. And you start coming up with wetsuit design, swim skin design, equipment design, things like that. Okay, so that's a little deeper dive on swimming. And now we're combining the kinematics and the kinetics to start doing a little bit more granular detail on understanding swim performance, and maybe why we would purchase a swim skin or a wetsuit, or why a wetsuit or different wetsuit models may be different than each other. All right, still scratch the surface, but we're getting deeper with each lecture. Thanks, everyone.